Okay. So, in the last class we are discussing this correlation matrices, and in that connection I talked about what is called Hermitian matrices and Hermitian transposition and things like that. So, today we continue from there. So, just to recall what we did last time, given a matrix say A, we define its Hermitian transposition as AH, okay, which actually is nothing but A conjugate, that is complex, take the complex conjugate of each entry of A and their transpose, which is also equivalent to doing it the other way. First take the transposition of A and then a complex conjugate. Okay. That is very simple. So, if A is not a matrix, but just a vector, say column vector, then its Hermitian transposition is what? You first transpose it, so it becomes a row vector and then take the conjugate of each element. Similarly, if A is a row vector, then its Hermitian transposition will be a column vector with all the original elements are complex conjugated. Okay. If it so happens, if A is a Hermitian, then A is called a Hermitian matrix. Okay, meaning suppose A is like this, A11, they are all complex entries, A11, A12, A1 say N, and what is AH? You take the transpose and then conjugate. So, A11, A21 star dot 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 AN1 star then A12 star, of course, it is A11 star 2, A22 star. See, the elements, diagonal elements do not change their positions upon transposition. Okay. Then AN2 star dot dot dot. Okay. A1n star. So, A1n comes here. Okay, actually on transposition I comma jth element, that is ith row and jth column element becomes jith element, that is jth column and ith row. Okay. Okay. Now, if it so happens that A is such a matrix that A and its Hermitian transposition they are same, then we will call A, we will say that A is a Hermitian matrix. Okay. That means A11 and A11 stars would be same, that is similarly A22, A22 star are same. So, that means that the diagonal entries are real, and A12, A21, A12 is A21 star, that is A12 in the matrix A itself, the ijth element and jith element, that is 1 comma 2th element, that is A12 and 2 comma 1th element A21, they are complex conjugate of each other. Okay. If that happens, that is Aij and Aji, they are same in magnitude and reverse in phase, that is Aij is Aji star. Okay. This is the key relation. Then the matrix A will be called the Hermitian matrix. Okay. Now, Hermitian matrices play a very important role in this all probability statistics, stochastic process, and any signal processing operation which is based on this stochastic process concepts, statistics concepts. Okay. So, this matrix satisfies many properties, and we will investigate some of those properties, we will discuss them. Okay. Now, in the previous lecture we have seen that if you have got two matrices which can be vectors also, and there is a product A B, and then the product matrix is then transposed using the Hermitian transposition, then this is nothing but take the conjugate of the Hermitian product matrix first, take the transposition and then conjugate, and then we know A B transpose is nothing but B transpose A transpose conjugate, and you know conjugate of a product, after all this realtic matrix will consist of terms which are products of terms elements from A and B, or B and B transpose and A transpose. Okay. And in the conjugate on each product is nothing but product of the conjugates. So, if you do that, it becomes B transpose conjugate times A transpose conjugate, and B transpose conjugate or B conjugate transpose they are same, which is nothing but B Hermitian and then A Hermitian. So, like ordinary transposition, Hermitian transposition also follows a similar rule on product matrices, that is A B H is same as B H A H. Okay. All right. Why we are interested in Hermitian matrices is this. Suppose a random vector, meaning actually we had a sequence of n elements x1 which is a random variable, followed by the element x2 which is a random variable, dot 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 dot, last element is xn which is again a random variable. Okay. We form a vector using this x. Now, first we define the mean vector, mu vector, that is expected value of x. Okay. What is expected value of x? That is E of x1 dot 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 E of x2 x n, okay, that is equal to mu 1 mu 2 dot 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 mu n. Okay. Then with these definitions you define a matrix R. As I told you last time, whenever I have a matrix, I will denote it by an uppercase letter like this capital R with an underscore, and whenever I have a vector, I will denote it by a lowercase letter with an underscore, underline, and when no underline is present, irrespective of whether I use a capital letter or a lowercase letter, it will be a scalar. Okay. Suppose I define R as E x Hermitian. What does it mean? In fact, R is called correlation matrix. Okay. What does it mean? E of, there is one vector x1 x2 dot 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 up to xn, and there is another vector upon Hermitian transposition we have got x1 star x2 star dot 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 xn star. Okay. So, that means you have got such elements, you can call it R11. I will tell you what is the definition, what is the meaning of capital R11, R12 dot 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 R1n, then R21, R22 dot 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 R2n, then Rn1, Nn. Okay, where this is your R, I write here, where Rij is actually the correlation between ith and jth random variable, defined like this. As I told you in one of my earlier lectures, recent lectures, as that I mean, we can define the correlation between complex valued random variables like this. Okay, E of xi xj star. Obviously, you know Rij, and what is Rji? Rji is xj xi star. And quite clearly, if you take a conjugate of this, you get this relation Rij and Rji, they are conjugate of each other. So, R12, R21 star, R12 and R21, one is the conjugate of the other. That is, you can say R12 is equal to R21 star, R13 equal to R31 star, and like that. This also shows that R11, R22 up to Rnn, they are all real numbers. Obviously, because if R11 and R11 star they are same, there is a number and its conjugate are same, that means the number has to be real. You can see it here also. What is Rii? That is E of xi xi star, which is E of mod of xi square, and mod of xi is always real valued. Okay. So, E of mod xi square. So, you can see that the diagonal elements are all real and in fact non-negative, and on all the non-diagonal elements they satisfy this symmetry relation, conjugate symmetry relation rather. There is Rij, there is a ith row and jth column, that entry is Rij, and the jth row and ith column, that is Rji. So, Rij and Rji, they are conjugate of each other, okay, which means R is a Hermitian matrix, that you can see when otherwise also. What is RH? That is E of H. You can push the Hermitian operation inside, because if after taking the whether you take the expectation of this matrix and then take the complex conjugate transpose, or you first take the conjugate transpose and then take the expected value, you will either way you will get the same values, right. So, this is nothing but E of and now previously we have seen a product A B Hermitian is nothing but B Hermitian, this is B, X Hermitian is B, X is A. So, A B Hermitian is nothing but B Hermitian, that is Hermitian of X Hermitian, and then this X Hermitian, right, and two Hermitians cancel, you get back X. So, you get X, which is same as R, which means R is a Hermitian matrix. Okay. Hermitian matrices have some very interesting properties. I am coming to that. Properties which are extensively used in signal processing applications. I will be coming to that. Along with the correlation matrix, you can also define covariance matrix. C is nothing but R minus M, where M is a matrix which is nothing but mu Hermitian. Okay. That means we have got X Hermitian here. Okay. You can also bring mu Hermitian inside the expectation operation, because after all these are constants. So, expected value of these constants will be the constants themselves. So, you can as well bring them inside these. So, now what happens? You have one matrix here, another matrix here. This matrix minus this matrix, X minus mu H. Okay. You can consider the total matrix. And what is the total matrix? It is a matrix whose say ith row and jth column What will be the element? It will be xi xj star minus mu I mu j star. Okay. And what is this? This is the covariance between the two random variable xi and xj. After all, what is covariance? We have seen what is Cij. Cij is nothing but okay. And you expand it. So, you get first term xi xj star, expected value of that, which is nothing but r I j, then minus mu I, expected value of xj star, which is mu j star. In fact, we have done this already. So, that is why I am not getting into details. Mu I mu j star minus e of xi times mu j star, which is again mu I mu j star, and the cross term mu I mu j star, expected value, it does not make any difference because these are constants, plus mu I mu j star. So, this cancel and you get this. Okay. And that is what you have here, expected value of xi xj star, which is r I j minus mu I mu j star. Okay. So, you get covariance, and obviously covariance, if all the elements x1, x2 up to xn, they are uncorrelated with each other, then we know their covariance, mutual covariance would be 0. What happens to this covariance matrix then? Mutual covariance, that is all Cij equal to 0 whenever I is not equal to j, and whenever I equal to j, then it is of course non-zero, because it becomes just the variance, that is E of xi minus mu I times again xi minus mu I star, xi star minus mu I star. So, that it becomes actually E of modulus xi minus mu I square, okay, which is the variance, right. In that case, so I write it mutually uncorrelated, then Cij equal to 0 if I not equal to j, and is equal to what? Sigma I square, which is nothing but E of mod xi minus mu I square if I is equal to j. So, that means C matrix, which is R minus M, this then takes this structure. All non-diagonal entries are 0, that is whenever I is not equal to j, this is 0, and diagonal entries consist of the variances. So, it becomes just a diagonal matrix like this, big 0 0, that means the upper half and lower halves are zeros, only diagonal entries which are positive numbers, non-negative numbers. Okay. So, that defines the covariance matrix for a set of mutually uncorrelated random variables. Okay. And in fact, if the means also are 0, if these random variables x1 to xn are given to be not only mutually uncorrelated, but also are of 0 mean, then of course, the M becomes an all 0 matrix, okay, except for the diagonal entries. No, it becomes a all 0 matrix, because after all the means are 0. So, in that case R is simply this. Okay. Now, Hermitian matrices satisfy some properties. Number 1, all eigenvalues are real. First, real and non-negative. Okay. How to show that? That means, suppose R x is an eigenvector is lambda x. Mind you, by definition of the eigenvector, x is a non-zero vector. After all, if x is a zero vector, all zero vectors are eigenvectors that way, because R times any matrix times a zero eigenvector is always a zero vector is always a zero vector. That is, so zero vector is excluded from the definition of eigenvectors. Okay. So, that means, whenever I have an equation like this, I say x is an eigenvector corresponding to the eigenvalue lambda for the matrix R, and x is thereby it is implied that x is a non-zero vector. Okay. All right. So, I have to show that since R and are Hermitian, they are same, that is R is a Hermitian matrix, x lambda is real. Okay. Lambda real. It is very easy. You take the Hermitian transposition of both sides. This leads to what? As I told you, product of two matrices, if you take the Hermitian transpose, you get x Hermitian or Hermitian. And again, lambda, you can view lambda to be a vector with single entry lambda. So, its conjugate its Hermitian transposition is what? You first take the transpose, which is lambda itself, because it is a scalar, and then conjugate. So, you get lambda star. And x Hermitian means, you have to take the Hermitian of x first, x Hermitian lambda star. But here it does not matter, because lambda star also is a scalar number. So, scalar number you can write to the right of x h or to the left of x h, does not matter, because it is a scalar number. But we have known that we are given rather that R is a Hermitian matrix, which means R Hermitian transpose is same as R. Okay. That is, since R is Hermitian, R H is same as R, which means lambda, which means here x h R is same as lambda star into x h. So, this is a row vector after all, x h is a row vector followed by a matrix, multiply you get a row vector. Similarly, on this side also row vector given by x h, each entry is multiplied by lambda star. So, if I now post multiply this row vector by a column vector say x, here also I bring x, but R x is we know lambda x. Okay. That means R x is lambda x. So, x h and lambda can be taken outside because it is scalar. So, and you take this to the take both the sides to the same side. So, lambda minus lambda star x Hermitian x is 0. R x is lambda x. Okay. R x is lambda x. So, you get this, put lambda x here, take lambda outside. So, x Hermitian x, here also x Hermitian x, take that common, lambda minus lambda star. Now, x Hermitian x is what? What is x Hermitian x? what is x Hermitian x? That is simply, if you just expand it, write x Hermitian as a row vector with each entry conjugated and then followed by a column vector x. Carry out the row vector times column vector multiplication, you will get so which is a real number because you are taking mod and then square. So, it is always non-negative. In fact, it is most of the times positive. It is if it is 0, each of the term has to be 0 because you are taking mod of square, which means x 1 must be 0, x 2 must be 0 and x n must be 0. They all should be having value zeros. But point is, by definition, x cannot be a 0 vector because x is an eigenvector. If x Hermitian, say in this product lambda minus lambda star times x Hermitian x is 0, x Hermitian x is a scalar, lambda minus lambda star is a scalar. So, either lambda minus lambda star equal to 0 or x Hermitian x is 0. But what is x Hermitian x? We have seen here mod of x 1 square plus mod of x 2 square plus dot 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 plus mod of x n square. So, this is as such greater than equal to 0, it cannot be negative. But if x is given to be an eigenvector, then it is not only greater than equal to 0, it is actually greater than 0, because an eigenvector means it is a non-zero vector. So, at least one entry has to be non-zero, whose mod square is not, of course, greater than 0. That means, in here x h x cannot be 0, which means lambda equal to lambda star. So, this leads to lambda equal to lambda star, which means the eigenvalues are real. Next thing we have to show that they are not only real, they are non-negative. Okay, we are coming to that. Now, the fact that they are non-negative, I postpone it for the time being. There is some property will be required, which I will be coming to little later. That property is called positive definiteness of the correlation matrix. So, I have so far proved that lambda is real. The fact that lambda is also non-negative is greater than equal to 0, I will be proving just a little later. Okay, I come to the other points. Property number 2. Sorry. It means, suppose or x 1 is lambda 1 x 1 or x 2 is lambda 2 x 2, and lambda 1 and lambda 2 they are not same. That is, x 1 and x 2 they are eigenvectors, all right, but they are eigenvectors corresponding to two different eigenvalues of R. One is lambda 1, another is lambda 2. Then it says that x 1 and x 2 are orthogonal, meaning if you take this product, which is called the inner product x 1 h x 2, this must be equal to 0, which is also true for x 2 h x 1. That is, you either make x 1 a row vector and then conjugate it and then multiply with x 2. So, what are the entries? X 1 star x 2 plus, okay, the first entry conjugate times the first entry of x 2, that first entry conjugate of x 1 times second entry conjugate for x 1 times second entry of x 2, and like that, with sum equal to 0. Or alternatively, in fact, if you take the Hermitian transposition of the left hand side here, you get x 2 h x 1, and obviously 0 Hermitian transposition gives you 0. So, x1h x2 or say x2h x1, they both give rise to 0. Okay. All right, this is to be proved. In fact, this orthogonality comes from a notion of what is called inner product. We define for two vectors inner product is like what in 3-dimensional world you had for dot product between two vectors. Let us take two vectors and get a real number out of the dot product. It satisfies some basic properties. For two vectors actually we define like this. There you write one vector then dot y, but a more widely used notation is this inner product or dot product. Instead of having just x dot y, we write within these two symbols, okay, x comma y, which is nothing but x Hermitian y. So, that means one is this vector x1 star up to say x p star if there are p entries, another is y1 dot dot y p, which is nothing but summation x I star y I equal to 1 to p. If the inner product is 0, then we say x and y are orthogonal. You have to prove that two eigenvectors x1 and x2 corresponding to two different eigenvalues lambda 1 and lambda 2 of R, they are mutually orthogonal. Okay. Now, how to show that? As I said, R x1 it is given lambda 1 not equal to lambda 2. Now, you take the Hermitian transposition of the first equation. Okay, that is now you take Hermitian transposition here. What do you get? x1 Hermitian, R Hermitian, but R Hermitian is same as R, never forget that. Is same as x1 Hermitian, lambda 1 Hermitian, but lambda 1 is a scalar, its Hermitian is a conjugate of lambda 1, and you can always write it in the beginning only because it is a scalar number. So, lambda 1 star x1 h, which also means as before, R h and R are same, so I am just writing like this lambda 1 star. Okay. So, I now post multiply this row vector with x2. So, I bring an x2 here. I have to do the same here also. But lambda 1, as I told, this is very important, lambda 1 is eigenvalue is real. So, lambda 1 star is same as lambda 1, isn't it? Because they are real, I have just now proved just a while back. That is lambda 1 star, they are same real. So, I write lambda 1 x1 h and then x2 is present, okay, and R x2 as given in the second equation is lambda 2 x2, replace R x2 by lambda 2 x2, take all the terms to one side. So, you get lambda 2 minus lambda 1 times x1 h x2 equal to 0. Which means since lambda 2 and lambda 2 are not same, this means only possibility is that this is equal to 0. Okay. Now, I come to positive definite. definite or non-negative, this is a more general case, non-negative definite matrices. Here positive definite I call it PD and non-negative definite I call it ND. So, this is ND abbreviation and this is PD. Or, so matrix R is PD first, positive definite if number 1 R equal to RH, that is R is Hermitian. And secondly, for any non-zero, most importantly, any non-zero vector A, the scalar number A Hermitian or A is greater than 0. Okay. Not only this is, of course, this is real, real and greater than 0. Okay. And then I add R ND if R is non-negative definite, condition 1 remains same, that is R has to be R Hermitian and A Hermitian or A, instead of greater than 0, it will just become greater than equal to 0. Okay. For all non-zero A non-zero. So, only difference is this, in the case of positive, see both in the case of positive definite as well as non-negative definite matrices, R is Hermitian. In the case of positive definite matrices, what we have, that if you take any non-zero vector A, then A Hermitian or A is a scalar number which is greater than 0, okay, of course real, and if it is a non-negative definite matrix, then A Hermitian or A is greater than equal to 0, still real. Okay. So, I consider non-negative definite matrices, and then in fact, because that is more general. So, I mean you can easily consider positive definite case as an extension of that. Okay. Then my statement is R correlation matrix that is, so long I was considering a just general Hermitian matrix, there was no connection with correlation matrices and all that. Okay. I considered a general Hermitian matrix and got those properties. Now, I am coming to R. Okay. Or maybe I first prove that if R is non-negative definite, okay, actually I made a small mistake. I mean, I said that for a Hermitian matrix, eigenvalues are non-negative definite, greater than equal to 0. That is not true as such. Actually, at that time I had in mind what is called correlation matrix, which are always non-negative definite. That I am coming now. Okay. So, I just correct my statement. Small correction actually. For Hermitian matrices, values are real. For PD matrices eigenvalues are PD and then within bracket ND, either PD or ND. Eigenvalues are real and positive within bracket non-negative. That is, if it is a non-negative definite matrix, eigenvalues are real. Not only that, they are greater than equal to 0. That is, they are not negative. But if it is positive definite matrix, eigenvalues are of course real and they are strictly positive. But this happens if the matrix is positive definite or non-negative definite. That is not just Hermitian, but that additional condition is present. If it is simply Hermitian, we can only say that eigenvalues are real. So, previously I made a statement which was not fully correct, because I just consider Hermitian matrices. Actually, I had in mind what is called correlation matrices. Correlation matrices, I will now show that they are actually non-negative definite matrices. Okay. Now, how to show this part, that if the matrix is non-negative definite, eigenvalues are, of course, they are real, you have shown, but they are also non-negative, that is greater than equal to 0. So, suppose R is given to be non-negative definite. Now, R x, as we have said, is lambda x, suppose. Then I just pre-multiply it by x Hermitian. So, what I get here is x Hermitian x. Okay. Now, by definition, x is an eigenvector of R, which means x is a non-zero vector. And since R is given to be non-negative definite, any x Hermitian R x for a non-zero x must be greater than equal to 0. Must be, yeah. It is non-negative definite. If it is strictly positive definite, it is strictly greater than 0. If it is non-negative definite, it is greater than equal to 0. Okay, which means lambda times x Hermitian x is greater than equal to 0. Lambda times x Hermitian x. But we have also seen what is x Hermitian x. That is, you take each component of x to the mod of that and square and sum. So, that is always greater than 0, because x is a non-zero vector. So, at least one entry will be non-zero. So, its mod value is positive, square is positive, which means x Hermitian x cannot be 0, which means cannot be non-negative, cannot be negative, okay, cannot be negative or cannot be 0, which means lambda has to be greater than equal to 0. See, x Hermitian x is always positive, because x is eigenvector. So, no, it is not that x can be 0, that there will be at least one entry of x which is non-zero. So, mod square of that is positive, which means x Hermitian x is always positive, strictly positive. So, lambda times that, if it is greater than equal to 0, the only conclusion is this. So, if this is greater than equal to 0, this only means lambda has to be greater than equal to 0, and lambda is real, you have already seen. And if it is positive definite, then instead of greater than equal to, we have the symbol greater than. So, in that case lambda is greater than 0. Now, I am coming to my main issue, which provoked me actually to get into the properties of Hermitian matrices or positive definite matrices and all that. That is R, which is a correlation matrix is non-negative definite. Now, first part of this is that R must be Hermitian, which we have already proved, we have dealt with at length. So, I am not coming to that. We have to come to the second property, that is for any non-zero vector x or a Hermitian R a is a number which is non-negative, either 0 or positive, but it is a non-negative number. How to show that? So, you take a to be a non-zero vector, take as before a is a non-zero vector, that is a vector whose at least one entry is a non-zero element. Okay. It is not that all entries are 0. Then what is a Hermitian R a? For any such non-zero a, if a Hermitian R a is first real and then greater than equal to 0, then we can say that R is non-negative definite, because R is Hermitian, we have already proved. Now, what is A Hermitian A? You can write, but mind you, A is constant, A is not random. You have just picked up some vector A by your choice, but there is no random element in it. Now, R is, as we know, E of and then A. Since the elements of A are constant, you can bring them within the expectation operation, it does not change anything. So, you can write it like this, A Hermitian X, maybe you can put it in a bracket, and then X Hermitian A. Now, A Hermitian X, this is a scalar number, right, row vector, column vector, and you can see what is X Hermitian A. This is nothing but complex conjugate, after all this is a scalar number, and if you take the Hermitian transposition, just a minute, this is what we can write, that is X Hermitian A is nothing but Hermitian transposition of A Hermitian X. If you really take A Hermitian X and take the Hermitian transposition of that, X Hermitian comes first, A Hermitian which is A comes second. And remember that A Hermitian X is actually a scalar number. So, its Hermitian transposition is nothing but, there is no transposition involved here, only complex conjugation, which means this gives rise to E of mod AHX square, which means this is a real number first, because there is a mod involved and mod square. So, it cannot be, expected value of this cannot be negative, it is greater than equal to 0. So, it is non-negative definite. If it so happens, we can ensure that it is always greater than 0, then we can also say R is positive definite. Now, when can we do that? Before that, consider this. If I say that expected value of a random variable, say x or say z, expected value of z is 0. That means z is a random variable which always takes the value 0, then only its expected value will be 0. Okay. Now, if R is non-negative definite and not positive definite as such, that means expected value of this mod square of AHX, this is, as such we know this has to be greater than equal to 0, but if it is non-negative definite, it means that you can find at least one A, one non-zero A, for which AHX, which is the random variable, it takes 0 value always, then only its mod square expected will be 0. I repeat again, if his R is given to be strictly non-negative definite and not just positive definite, that means for some A, that means it is not just greater than 0, it is greater than equal to 0, which means sometimes it can be equal to 0 also, but when it is equal to 0, that means for some A, that is there you can find at least one A, if not more, for which, and A is non-zero, for which AHX, it turns out to be 0 always. Okay. Then only its mod square upon expectation also would always give rise to 0, and you can put an equal to 0. When does that happen? That leads to linear dependence and independence. This set x1, sorry, is linearly independent if it is linearly independent, that means no relation, there is no linear relation involving these random variables. Means any of the no random variable here from x1 to xn can be written as a linear combination of the rest. Okay. Then it is called a linearly independent relation, which means actually using vector space theory or linear algebra theory, it means that if you really want to form a combination like a1 x1 plus a2 x2 plus dot 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 an xn equal to 0, then the only way you can do is that a1 equal to 0, a2 equal to 0, dot 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 an equal to 0. Okay. That is, you can easily see, suppose, I mean what I mean here is this, if you really form an equation like this equated to 0, that means if you linearly combine these linear variables and equate it to a 0 random variable, right hand side is a 0 random variable, which means it always takes the value 0. If you really want to find out such a1, such a2 and such an which maintains this equality, then if they are linearly independent, the only way you can do is by putting a1 equal to 0, a2 equal to 0, n equal to 0. According to me, under this condition, you can never express any of the random variables x1 as a linear combination of the rest. Suppose, just to give an example, suppose a1 is a1 and a2, they are non-zero and rest are 0. That means a1 times x1 plus a2 times x2 will be equal to 0. So, x1 will be, you can always write x1 in terms of x2, or say a1 not equal to 0, a2 not equal to 0, a3 not equal to 0, rest are 0. You can then write a1 x1 plus a2 x2 plus a3 x3 equal to 0, other elements are already become 0. So, x1 then you can keep on the left hand side, right hand side, I mean you push x2 and x3 terms. So, you can write x1 in terms of x2 and x3 as a linear relation, okay, so on and so forth. In fact, suppose if a1 is only one element, a1 is non-zero, others are 0. In that case, you have got just a1 x1 is 0. That means, since a1 is non-zero, x1 equal to 0. That is, x1 is the 0 random variable. And a 0 random variable, you know, if you have a 0 random variable in this set S, then the set is not linearly independent, because 0 random variable can always be written as a linear combination of the rest. Just multiply each of the random variable by scalar 0, 0 times x2 plus 0 times x3 plus dot dot 0 times xn, okay, that makes it a 0 random variable. So, just to test whether a set of random variables are linearly independent or not, form an equation like this with a1 to an being scalars equated to 0 random variable. See what choice of a1 to an can give rise to, can maintain this equality, and if it is such that only possibility is by taking a1 equal to 0, a2 equal to 0 up to n equal to 0, then you have this. Okay, you can say they are linearly independent. If they are linearly independent, then you can also see that any subset also is linearly independent. That is easily seen, because if the subset, if in the subset you cannot express, you can express some element as a linear combination of the rest, then that applies to the entire set also, because a linearly dependent set, okay, a linearly dependent subset in a bigger set, that makes the overall set also linearly dependent. Okay. On the other hand, if you can find out some coefficients a1 to an where not all are 0, okay, but this equality is maintained, then you say this set is a linearly dependent set, which means some elements, or at least one element, can be expressed as a linear combination of either the whole of the rest or part of the rest. Okay. Now, in fact, I am running short of time, so I will be winding up soon. That means, if linearly independent, that means expected value of any x1, you take the mod square, this has to be greater than 0 if A1 not equal to 0, A2 not equal to 0, dot dot dot, AN not equal to 0. Because if they are not equal to 0, this cannot be a 0 random variable, and if it is not 0 random variable, its expected value of the mod square has to be greater than 0. Okay. So, I stop here today. From here, I will continue in the next class. So, we will conclude with this remaining properties of the correlation matrices and all that. Okay. So, thank you very much. Okay. So, in the last class, we are discussing this correlation matrices. We discussed some properties of Hermitian matrices, or Hermitian matrices which are also, positive definite matrices. Okay. We found out again Hermitian matrix as such, not even positive definite, they are always real, okay, and their eigenvectors are orthogonal to each other. Okay, we have found it out. Then if in addition the matrix is given to be positive definite, then eigenvalues are also positive. If it is non-negative definite, they are non-negative. Okay, this we have seen. Okay, then we are discussing the linear dependence and independence of random variables and all that. So I just start from there. I continue with the previous discussion on the correlation matrices first. Okay. Do you remember our previous treatment on what is called vector space of random variables, where each random variable was treated as a vector in an abstract vector space of all possible random variables in the world. Okay, and there we defined addition of two random variables as addition of two vectors. What is meant by 0 vector? That is a random variable which always takes 0 values. Okay, then negative of a random variable means it's again a random variable which takes negative of the original random variable, and likewise it's just in that framework we can discuss determinant of T times determinant of D times determinant of TH, which is nothing but T inverse. And these two cancels, determinant of T inverse, they cancel. So, you get back determinant of D. And what is determinant of D? It is the product of eigenvalues, lambda 1, lambda 2, dot dot dot, lambda n. As we have seen, if the eigenvalues are firstly real, so determinant of R is always real, that is done. And if they are all positive, if the eigen matrix is positive definite, then each is positive, so determinant is positive. Okay. So, that is all for today. We continue from here in the next class. Thank you very much.